Good afternoon, guys. So today I'm gonna do more examples on MLEs when you have two parameters. When you have two parameters that are not known, right? I know I did some examples yesterday, but I'm gonna do yet more examples today. I think the more examples, the better. The more examples, you learn better, guys. Okay? Are you guys listening or what? So the first example I'm looking at today is the following. You have a random sample from a uniform distribution on the interval a to b, and both parameters a and b are unknown. And we want to find the MLEs of a and b. So the procedure is as follows. The first thing you do, you guys know that the density of the uniform distribution from A to B is, if you look back on the lecture notes, you will see is 1 divided by B minus A. So what you have is 1 divided by this, right? Take the log of the likelihood. Take the log of the likelihood, you get this, right? And then you take the partial derivative, first with respect to A, and then with respect to B. Right? With respect to A, the partial derivative is with respect to B. Right? Are you guys with me? Yeah? So this is the partial derivative with respect to A. This is the partial derivative with respect to B. Set this to 0. Set this to 0. Call this 1. Call this 2. 1 implies that B minus A is either plus or minus infinity. 2 implies B minus A is either plus or minus infinity. Right? So that means, what does this mean, guys? It means that the standard approach right? It means that the standard approach for finding the MLEs doesn't work. Now, in this situation, what do you think? What should we do? I think I told you this last week. When the standard approach doesn't work, what do you do, guys? Indicate a function, exactly. So that's what I'm going to do now, guys. The standard approach clearly doesn't work, right? So I'm going to use the indicator function. So try try the indicator function approach. So I'm going to rewrite the likelihood function as the product of 1 divided by b minus a. Now remember, a uniform random variable is defined between a and b. That is, every xi must be greater than a and less than b. So I must say that here, guys. So I must say that a is less than or equal to xi, less than or equal to b, because that's the definition of the uniform distribution. By definition, every xi must be between a and b, right? So this is this is the principle of indicator function approach. So this becomes this. Now, what we have here is a product of indicator functions. I think I told you about a week or two ago how to simplify products of indicator functions. If you were not here, just look back in the scan notes, guys. Right? So if you look back in your notes, you will see. I'm not going to repeat the rules once again. I think I wrote them down on the piece of paper, guys. So if you don't have them with you, just look back in the scan notes online. Okay? So this will simplify to the following, guys. It will simplify to this. That's issue. By one of the rules I mentioned in the lectures some time ago. Once again, if you don't have the rules with you, please look back in the course website. You will see the rules. Okay. So this simplifies to this. Now, let me put this here, guys. So let me. What I'm going to do is the following now. Because we have two parameters, a and b, we need two graphs, right? The first graph is versus A, the second graph is versus B. And on both axes, you're trying to plot you're trying to plot the likelihood function of A and B with respect to A and with respect to B. Right? Now this is where the knowledge of graphing function comes in. I'm sorry once again. If you have difficulties, I can help you outside the class, but not within the lecturing hours, because this is kind of stuff you should have already learned in your calculus course. But if you have difficulties plotting graphing functions, I'm most happy to help you guys outside during exam classes or any other time. But if you plot this versus A, how do you think it will look like? If you plot this function here versus A, all right. Let me give you an idea. Suppose this is your min of xi. Okay, and suppose this is your max of xi. Now, this function here, it says that a must be less than or equal to the min of xi. All right? But if a increases, b minus a will decrease, right? And 1 over b minus a will increase. So the graph will look like it will be an increasing function up to this point, and as soon as you pass this point, it will be zero. Do you see how I got this graph, guys? This is what I have drawn here is the graph of this function here versus a. Yeah, is that clear or not? Yeah. I mean, this is once again stuff. I mean, you should have. I don't want to repeat this again, but I mean, if you have difficulties graphing function, it's something you should work on, and I'm prepared to help you guys on it. All right. So, and if you graph this versus a, this is how it will look like. Now, okay. Now let's look at this one, guys. Versus b, it says that b must be greater than or equal to the max of xi. Okay? But this one, if b increases, the denominator increases, and 1 over the denominator will decrease. So this here is a decreasing function of b, right? But on the other hand, we must have b greater than or equal to the max of xi. Therefore, the graph will look like this. It will be a decreasing function following this point, and before this point, it will be zero. Is that clear, guys, or no? Yeah? So the graph of the likelihood versus A looks like this, and the graph of the likelihood versus B looks like this. Now, to answer the question is, what is the MLE for A and what is the MLE for B? Remember, the principle of maximum likelihood says the MLE for parameter is where the graph attains the largest value. This graph attains the largest value at this point, and this graph attains the largest value at this point. All right, and therefore, according to this graph, the MLE for A is the min of xi, and according to this graph, the MLE for B is the max of xi. Is that clear, guys, or not? So this answers the example. I mean, this is a really important example. I think I do this example every year, and some people have difficulties. Not some. I think quite a few people have difficulties understanding it, mainly because they are unable to graph the function. So therefore, it's really, really, really important that you learn how to graph functions, right? And okay. Any questions, guys? You all right? Yeah? Some people look lost, I don't know. Yeah, anyway, I will do more examples like this later on, but so that's one example. Example 2. Example 2 is suppose So once again, this is an example where you have two parameters, A and K, right? Both parameters are known, right? And we want to find the MLEs of both parameters. All right, so the first thing to do is to write down the joint likelihood function, which is the product All right, this is the likelihood function. The next step is to take, I'm doing this many examples. I want you to get a good, because mass and likelihood estimation is fundamental to any course in statistics. So any course that you would want to take in third year, for example, statistical inference or multivariate analysis, any course that you would, when you go into third year, that is next, I know some of you are already third years, but when you go next year, you need, every course uses maximum likelihood estimation. So it's really fundamental to any course you want to take in the future, right? Taking the log likelihood, this is the log likelihood. All right, now we do the partial derivative of the log likelihood with respect to A and then with respect to K. Let's do it with respect to A, it's going to be N by A plus all right, this is the partial derivative. And the partial derivative with respect to K okay. So these are the two partial derivatives. So set this to 0, call this 1, call this 2. All right, let me put it over here, guys. Now, from equation 1, we can say that A is equal to N, or A hat rather, A hat is equal to N all right. So this is so solving equation 1, this is what you get for A in terms of K. Now solving equation 2, if you solve equation 2, you get K, or K hat equal to plus or minus infinity, which does not make sense. So in this case, what I'm trying to tell you is one of the two equations gives a proper answer, but the second equation doesn't give a proper answer. This one looks okay, right? But this solution does look weird, right? You cannot have plus or minus infinity as a solution, right? So in this case, what you need to do is the following. So all right, I'm going to use, because there are two parameters, and with A we are okay. The standard approach appears to work okay for the parameter A, but for the parameter K we have problems. So I'm going to use the indicator function approach to find the MLE for the parameter K. Okay, so I'm going to rewrite. Are you guys with me or no? Yeah. So I'm going to rewrite the likelihood function. Right. If you look at the question, guys, just above here, it says here that every x must be greater than or equal to k, right? When I define the density function PDF, I say that x must be greater than or equal to k. So you must have the condition that xi, that every observation xi, yeah, is greater than or equal to k. Okay? Is that clear, guys? So we must put this indicator function, right? So this simplifies to okay. All right, guys. All right, now I'm going to use one of the rules I mentioned to you about a week or two ago to simplify this guy here, right? So if you remember the rule, let me test your memory, guys. What do you think this will reduce to? Just tell me, what do you think this will reduce to, guys? No, not really. Any other answers?
Minimum of xi greater than k?
Yeah, exactly, yeah. Just check the rules, guys. That's why it's really important. Just go back. I mean, you should look back in the course website. You will see the rules. There are 3 different rules, which are not really hard to not hard to remember. So this reduces to this. Okay, all right. All right. Now let me put this over here, guys. Now the next thing I'm gonna do, you know what I'm gonna do, guys. Right, I'm gonna plot this function here as a function of k. Now, how do you think it's gonna look like? Now, let me suppose this is the min of xi. Okay. The only term here the only term, apart from this term, the only other term that involves k is this term here. Now, if you look at this term carefully, is this an increasing or decreasing function of k? This one. This is an increasing function of k, right? And therefore, the graph will look like what? The graph will look like it will be an increasing function up to this point, and thereafter it will be zero, right? Because remember, k must be less than or equal to the mean. If k is greater than the mean, then this is 0. So the graph is an increasing function, and then it falls down to 0. So clear, guys? I mean, this is again, I keep telling my students, graphing functions is really important. Beyond, especially when it comes to maximum likelihood estimation, it's really, really important. So if you have difficulties, the only thing I can suggest is try doing examples, right? And that's the way you develop your confidence, guys, on graphing functions, right? Now, obviously, looking at this graph, the largest point is, this is the largest point of the graph, and therefore, the MLE for k is the min of xi. All right, guys? ML is the min of xi. And going back here, guys, we already got the MLE for a. The MLE for a is, to write it down, is, let me just copy this down, okay? Is just all right? So this is the MLE for k, and this is the MLE for a. Any questions on this example, guys? Yes? No? Is that clear or no? Yeah? There's one more example I would do today. This is number 3. Or maybe, yeah, okay, let's see. So here you have, once again, you have a random sample from a uniform distribution from mu minus delta to mu plus. This was this was one of the past exam paper questions, guys. All right, the first thing you need to do is to write down the likelihood function. Yeah, and this will be the PDF of this distribution is what? It will be 1 divided by 2 delta. Yeah. Remember the PDF of the uniform is 1 divided by b minus a. The b minus a here is 2 delta, right? Okay. taking the log of the likelihood, you get minus n to log 2 delta, partial derivative with respect to mu, partial derivative with respect to delta. All right? With respect to mu, it is 0. With respect to delta, is minus n over delta. One means nothing. Okay. 2 implies that delta is plus or minus infinity. Right? So once again, the standard approach doesn't work here. Okay? So we need to use the indicator function approach, right? Okay, so put it here. All right, so I'm going to try the indicator function approach, okay? So it's going to be the likelihood yeah. All right, now we know that the each xi is between this mu minus delta and mu plus delta. So we must say that every xi lies between mu minus delta and mu plus delta, right? And put this in like this. Okay? Now, you should simplify this, guys. You get all right. Now, once again, you need to test your memory, guys, here. Now, what you have here is the product of indicator functions. And using one of the 3 rules I gave to you about a week or 2 ago, you can simplify this, right? I'm not going to ask you again, but you should know how to simplify this, guys, okay? So this will be max of xi less than or equal to mu plus delta, comma, min of xi greater than or equal to mu minus delta. This is what you will get, right? If you simplify the product using one of the rules I gave to you, this is what you will get, right? Now, this you can write as follows. You can write this as I, that delta or delta All right? Let me put this here, guys. Now, let me show you now. I'm going to do this graphing thing again one more time. I know maybe some of you are getting bored about this, but it's really important that you learn how to graph things. Okay. Yeah. So let me show you. Right. Now, how do you think the graph will look like? If I plot the likelihood function L of mu comma delta versus delta, right? How do you think it will look like? I'm asking you to plot this guys here versus delta. Remember, okay, what can you say about this function here? This one here is a decreasing function of delta, right? So as delta increases, 1 divided by 2 delta power n decreases, right? But according to this function, according to this term here, delta must be greater than or equal to this and greater than or equal to this too, right? So the answer is to be as small. We want to choose delta as small as possible, so that it is we want to choose delta as small as possible, so that afterwards it is a decreasing function, right? And this is the largest point of the graph, right? You guys follow me or not? Yeah? This is the largest point of the graph, right? Because all right. Now, if this is the largest point, guys, then we must have both these satisfied. In other words, we must have delta equal to, or delta hat equal to, max of xi minus mu hat. Yeah, and we must have delta hat equal to mu minus min of xi. You understand where I got this two from, guys? We want delta to be as small as possible, so that the graph is as large as possible. You know, if the smaller the value of delta, right? The smaller the value of delta, the larger this point is, right? So the smallest, according to this inequality here, the smallest value for delta is this one, yeah? And according to this inequality, the smallest value for delta is this one. So you have two equations, right? Call this, say, equation 1. Call this, say, equation 2. You understand how I got these two equations, guys? Because we want delta to be as small as possible. And this guy here says the smallest possible value for delta is if this is equal to this. right? And this guy here says the smallest possible value for delta is if this is equal to this. Now what you need to do is to find the MLEs for mu and delta, just need to solve these equations. So what do? You do 1 plus 2. You should do 1 plus 2. You get 2 delta hat equal to max of xi plus min of xi. So delta hat is equal to the max of xi plus the min of xi divided by 2. Are you guys with me or no? Now you should do 1 minus 2. You have you have max of xi This is right, 1 minus 2. Is this minus? Yeah. Oh, sorry, I made a mistake here. This should be minus, right? Should be minus, yeah, thank you. Thank you for pointing this out. This should be minus, guys. Now, if you do 1 minus 2, guys, you have all right, so this implies that mu hat is equal to max of xi plus the min of xi divided by 2. So we got both answers. This is the estimator for mu, and this is the estimator for delta. I know this question is a little bit tricky, guys, but I hope you understood what I tried to say. Did you guys follow or what? No? The idea is that because this guy here is a decreasing function of delta, we want delta as small as possible so that the likelihood is as large as possible. Now, we have two different inequalities here. According to this inequality, the smallest possible value for delta is this one. Yeah? Now, according to the second inequality, the smallest value for delta is this one. So you have two different equations and two different unknowns and solve them. So this is what you got. This is the solution for delta, and this is the solution for mu. All right? Yes? All right. Now, I know we've got a few minutes left. The next thing I'm going to do, I think we've done enough examples on MLEs for 2 parameters. The next thing I'm going to do, I don't think I have time today, but I will just write it down so that you can think over this maybe tomorrow or over the weekend maybe. Now I'm going to do some examples on MLEs of theta with more than I'm going to do some examples. I'll just start one example today. Hopefully you can finish it by yourself, guys. Where you have not just one parameter, not just 2 parameters, but you have more than 2 parameters, right? All right. Now, the first example is the following. Right. So in this case, you have two samples, x1 to xm, coming from a normal distribution with these parameters. And then you have another sample, y1 to yn, coming from another normal distribution with these parameters. So basically, you have three parameters. You have three parameters, mu x, mu y, and sigma squared. And we want to find the MLEs of all three parameters, right? So the first thing to do, or just start it off, guys. The first thing to do, guys, is to write down the joint likelihood function of three parameters. So it will be the following. I'll just make the start so that hopefully you can complete it when you have time, guys. So this is the contribution from the first. This is the contribution from the first sample, and the contribution from the second sample. And this is the contribution from the second sample. All right? So the likelihood is the product of the contribution from the first sample with the product of the contribution from the second sample. All right, guys? And if you simplify this, this will become, let me see. All right, this is the simplified form of the likelihood. All right, now I'll leave it at this stage. Now try to complete this and see if you can find the MLEs of the three parameters, mu x, mu y, and sigma. Right? If you can't do it, then I will do it when I see you guys next Tuesday.
Because N and A are positive numbers. Yeah?
So by definition, for this distribution, A must be positive. A must be positive. Yeah, I should have said that. I should have said in my class, A is positive. So A is positive. So as K increases, this increases. Yeah. They're not different. Oh, they are different. Yeah, they are different.
Yeah, so why not, like maybe for example, like this one is smaller and this one is bigger, then we need to have both of these. The bigger one, then the maximum is like one of these. I just wonder why.
Yeah, both conditions must be satisfied, right?
Yes.
Because this is a decreasing function, right? You want to choose delta as large as possible, right? And according to this inequality, the largest possible value is this one. This is the largest possible value. And according to this inequality, the largest possible value is this one. And then we solve these two equations to get this
But
answer.
that means that we solve these two.
Yeah.
So I just wonder why these two are possible.
Because I want these conditions to be satisfied. Yeah, that's why they become equal.
Yes, I just want to for example, if they are not equal, then we need to
If they're not equal, they still come to one rule like this. You have to do it a different way. Yeah. This one. No? Why is it zero? It's this one here. Now k must be less than or equal to min, right? So it's an increasing function up to this point, and afterwards it will be zero. There's no k0 here. I'm just looking at relative to this point. When k is less than or equal to this, it's an increasing function. When k is greater than this, it is zero. Yeah, that's right. In the two parameter and the multi-parameter case, I don't want you to do that because it will take you a long time to do that. It's only in the one parameter case. You need to find the second order derivative.
I want to know how this is a decreasing function.
It's an increasing function. It's an increasing function because a is positive. I'm assuming, I know I didn't say that, but a is a positive function. A is a positive
How
function.
about the variable x?
You don't need to know that because there's only one k here. You can ignore this. You can ignore this because there's no k here. There's no k here.
But if this is negative, it is in the opposite direction.
Yeah. Exercise are assuming all these are positive. All these are positive.
So xi is positive. In examination, it will equal. So if this is negative, will it become decrease?
No, you cannot. Exercise cannot be negative matter. You must assume that this is positive. This is positive. Then this function will be an increasing function of k.
Thank you very much.
Alright. Sorry, madam.
Okay.
Oh, sorry.
There you go. That's yours. Is that your drink as well?
Yeah. Thank you. No, thank you.
so A must be
Yeah, A is positive, yeah. A is positive. Yeah, you have a question too.